Okay, so we have our data warehouse where we're collecting and organizing our historical data coming from all of these different data sources. Now, in a traditional extract, transform, and load scenario, all of the data in our warehouse has to conform to our predefined schema before we can load it into that data warehouse. Now, the challenge here is that in modern times, we actually have many other types of data sources we want to work with, like text and log data from machines and applications. We also have multimedia data and maybe user-generated content types of data. And this kind of data, what does ETL look like for this? What's the schema that we would want to apply to this kind of multimedia or semi-structured, unstructured data? And do we really, when we're loading it into our data warehouse, want to enforce a particular schema? Because once we've enforced that schema, we can't change it. And enforcing that schema might cause us to change the data in ways that are lossy. So here's an example of maybe how we might try to impose a schema on picture data. So we could extract out the EXIF data, the metadata associated with the picture. So when you take a picture, the camera records information like an ID and the date that it was taken and so on. And then maybe we also, as part of the transform step, run a neural network on it and tag the pictures with things like it's a cat, or is it a cat, or is it Grumpy the cat? And so, yeah, maybe this works, but I also have like backhoes here. And so do I want to add additional categories? Well, the categories are fixed when I actually load in the data. So I would have to add that as post-processing. And so again, do we really want to force a schema on our data when we're loading it in? The alternative to using a data warehouse is to use a data lake. And disclaimer here, definition of a data lake is still being defined, but it's a buzzword that you'll hear a lot. And the idea behind a data lake is as follows. We're going to store a copy of all of the data, our historical data, in one place. And we're going to keep it in its original natural form. So now the people who are actually using the data, the consumers of that data, they get to choose how they do the transform and how they use the data. And so we're now imposing the schema at read time instead of imposing that schema when we load the data. So naturally I could ask the question, well, what could possibly go wrong if we're imposing the schema at read time instead of at load time? So a little sidebar. This is the dark side of data lakes, right? It requires a real massive cultural shift in a company because you end up, instead of curating your data and putting it into this data warehouse in this very carefully managed form, we're just going to save everything. And so if you think about the curation process that you've done in this class, a lot of what you do with curation is you get rid of the bad data. You get rid of the invalid data points. You clean up the data. You get rid of the noise. But if we save everything, then maybe the noise begins to dominate the signal instead. And we're going to end up with limited data governance and planning, right? We're just saving everything. Anything you create, you throw it into the data lake. And so you're going to see files like hdfs/important/Joseph bigfile3.csv with JSON. What? So what's in that file? Not really apparent looking at it. It's a big file. Number 3. When was it created? Well, maybe there's some metadata of the file, but does that tell us when the data was created or merely when the file was created? And who created it? Well, it has the name Joseph, but is that Joey Gonzalez or is that Anthony Joseph? I don't know, right? And so we lose cleaning. We don't have cleaning. We don't have verification, which means we can end up with a lot of dirty data. And when I actually want to go and read that data, that's when I actually have to do my cleaning and my verification. And different people who are consuming that data might do different cleaning and different verification steps. That might be a positive, but that also could be a big negative for working with the data. It also means any consumers working with the data have to understand the cleaning and verification process. Whereas previously with the data warehouse, they got nice clean data, they could just work with the data. At the same time, however, they didn't understand what cleaning and verification was done, and so what particular biases might have been introduced in the cleaning and verification step. Maybe I care about the data that it looks bad because it's not really bad, but it represents some kind of error condition that I want to identify in the process, error in the process that I want to identify. So it means that you're going to end up with tools that are way more complicated because they have to do this cleaning and verification. It's not just generating SQL queries. And our old tools, of course, won't work because they required clean, canonicalized data. And so, how do we solve this problem? Enter the data scientist, right? And this really is the bright side of data lakes, right? With a data scientist at the helm, they bring new skills. They can work with distributed data. They can do the cleaning steps, the processing and cleaning steps that we need to do. They can apply things like machine learning, computer vision, and statistical sampling. And there are a lot of technologies that are coming to the fore for working with this kind of data. We have the ability now to run SQL over very large files, massive petabyte-sized data sets. We have self-describing data formats like Apache Parquet, and we have catalog managers that help us manage these collections of data. And organizations are evolving. So we're now starting to track how data is being used, where data is being created, and the permissions associated with that data for access and creation. And so now we have a new job title, data engineer, somebody who can manage these types of processes. So what do we give that data engineer? We give them lots of hard drives and we give them lots of CPUs. And so we can naturally ask the question, when we have these massive amounts of unstructured data sets, how do we store and compute on them? So we've got these large unstructured data sets. Well, there's some requirements, right? The first requirement is that we have to be able to handle very large files that are too big to fit on a single machine. So they're going to span across multiple computers. Our solution is we're going to use cheap commodity devices. But they're cheap, they're commodity, which means that they may fail frequently. Right? If we have large numbers of inexpensive devices, they're going to fail. We're going to have a device that fails pretty frequently. We're also going to use distributed data processing. So we're going to take advantage of all of these commodity devices to process the data quickly and easily. And there are solutions, right? So solutions like distributed file systems that spread the data across multiple machines. So now we can have very large data sets. The size of our data set is now only limited by how many machines we can stuff into a building. And we can stuff tens of thousands of machines with a lot of disk drives into a large building. Again, we're going to assume that machine failures are very common, and so we're going to store the data redundantly. So we're going to pay a price here. And the argument here is that the cost of duplicating the data, having redundant data, is going to be less than the cost of using enterprise computers and enterprise hard drives and so on. So that's the trade-off. We could use hardware that's more reliable and reduce our need for redundancy, but it would be a lot more expensive. Okay, second thing we're going to do is distributed computing. So we're going to load and we're going to process our files on multiple machines and do that concurrently. So now, instead of being gated by how quickly can I read from an individual hard drive, I can read from tens of thousands, hundreds of thousands of hard drives simultaneously. And so the total bandwidth is going to be very high. So again, we're going to assume that machine failure is common. And so for both the storage side, we need redundancy, but also for the data processing side, we're going to need redundancy. A machine might fail in the middle of one of these big computations. If that happens, we want to be able to quickly deal with that through redundancy. And so the approach we're going to take is a functional programming approach. We're going to use that functional computational pattern to give us parallelism. And we'll see how these three components work together to allow us to work with large unstructured data sets. So again, distributed file systems, distributed computation, and functional programming.